Hello everyone. In this problem we will be going over an IMO 1998 problem, problem number 4 to be exact. Here's a view of this problem. Determine all pairs of positive integers x and y such that x squared plus times y plus x plus y is divisible by the following expression in terms of x and y again. So what I will do is, let me first write down this condition here. So we have that xy squared plus y plus 7 strictly divides, I should say, x squared y plus x plus y here. What I will do is I will do the following trick. I would like to kind of in a way get rid of this very ugly expression here. So for that, what I will do is, if it is the fact that this thing here, xy squared plus y plus 7, divides this whole right hand side, I can it will continue to divide this times a number a, let's say a coefficient a, plus itself, xy squared, because it is very close, these expressions are very close to each other, plus y times b. All we need to do now is to figure out what are those a and b values. Well, it turns out that a is simply little y, and capital B, the coefficient b, is simply little minus x. So that's simply y, and that's simply minus x. So therefore what I claim is, so this implies that xy squared plus y plus 7 divides y times x squared y plus x plus y. So that will give us an x squared y squared here, minus x times xy squared, again an x squared y squared here. So therefore those terms will cancel out. Plus y plus 7, but that does the trick, so therefore those terms will cancel out, so we will have an xy here, a minus xy here, so those will cancel out as well. So finally I will have y squared minus 7x, so that's equal to y squared minus 7x. Now the rest of the problem is a case work. So we basically have 3 cases. The first case is obviously any number will divide 0. So what happens if y squared minus 7x is actually equal to 0? In that case, this would imply that x itself, or so let's say 7x is equal to y squared. So therefore so this would imply the following parameterization, if you will. X will be simply equal to 7k squared, and y is equal to 7k. So therefore this would be an appropriate parameterization that solves the problem. So therefore let's say all the pairs xy, which is equal to 7k squared, 7k, of this form where k is greater than or equal to 1 are solutions. So that's good. So that would be the first case. Let's have a look at the second case, where y squared minus 7x is strictly greater than 0. In this case, so that would imply that, because it's greater than 0, so the divisor here, so the divisor here, xy squared plus y plus 7 is definitely less than or equal to this expression here, y squared, squared minus 7x, and we also, obviously, so that's strictly less than y squared here, right? So that's obvious because minus 7x, x is a positive integer, but then y squared itself in its turn is strictly less than x times y squared, why? Because x is x is 1 or more, but then we have also some extra. That's why the strict inequality, y plus 7, which is a contradiction because xy squared plus y plus 7 is strictly xy squared plus y plus 7, so that's a contradiction. So therefore this case does not give us any solution. So there's only one final case to consider. So let me do it, well, let's do it on the next page, I guess. So as a final case, so let's call it case 3, we are looking at the case where y squared minus 7x is strictly less than 0, but then that would imply that our divisor xy squared plus y plus 7 is less than or equal to, so in inverted form, because this number is now a negative number, 7x minus y squared. And equivalently, I can rewrite this expression as x times y squared minus 7, which is less than or equal to minus y squared minus y minus 7. So therefore, our right-hand side is strictly less than 0. It must be the case that the left-hand side is strictly less than 0, suggesting that y squared minus 7 is strictly less than 0 as well. So, which means y squared, so this implies that y squared is strictly less than 7, suggesting or y is equal to 1 or 2. So let me erase this thing here. So now I have two additional case work, so let's call it 3.1. So in this case, let's assume y is equal to 1 here, the first case. This would give us x plus 8 divides x squared plus x plus x squared plus x plus 1, and from here, again, we can make a similar trick, a very simple trick. X times x plus 8, obviously, minus 7 times x plus 8 plus 57, I guess, so that should work. X squared, so that's correct. So plus 8x minus 7x, that works. Minus 56 plus 57 is plus 1, so that's correct. But then if x plus 8 obviously divides the whole thing, it divides the first term, the second term, it must divide 57 as well. So this suggests that x plus 8 divides 57, which is simply 3 times 19. It must be that so this implies that x plus 8 is either equal to 19 or x is greater than 0 or 57, suggesting that x is equal to 11 or 49 actually. So that would give us two additional solutions, obviously. So therefore our other solutions would be 11, 1 and 49, 1 as well. So our solutions, so additional solutions. So far, if you remember from the first case, we had a parameterization solution. Let me remind you that the parameterization was all the pairs xy in the form 7k squared, 7k, where k is greater than or equal to 1 are also solutions. And finally, the case 3.2, where y is equal to 2 here, would lead to 4x plus 9 divide x plus 22. But then from here you will easily see that this implies that 4x plus 9 is less than or equal to x plus 22, suggesting that x itself is less than or equal to 13 over 3, which turns out to be another contradiction as well. So the contradiction follows from the fact that that would suggest x is equal to 1, 2, 3, or even 4, and y is equal to 2. It's easy to check that none of these four solutions or cases work actually. So that suggests that the only solutions are the ones given here. That concludes our proof. Hope to see you in our next video.